Hi, I'm Kayla, the data developer and analyst.
Hello there, my name is Melvin Houston, and I am the hardware engineer for the Community Gardens project.
Hi everyone, I'm Niyati Ajmera, and my role is of a full-stack software engineer on the Community Garden project.
Improving food security in local communities and providing access to healthy, locally grown foods are major goals of the Community Gardens movement. Our research began as an attempt to address the fresh food needs of people who live in food deserts. According to the CDC, food deserts are areas where people have limited access to healthful and affordable food. This may be due to having a low income of having to travel farther to find healthful food options. Community gardens can provide neighborhoods and communities with access to local spaces that can be cultivated for growth of communally grown fruits and vegetables that can provide food and support to members of the community. Faculty at Cal Poly Pomona who organize community gardens and who facilitate service learning projects with students have mentioned the challenge of being able to know which garden locations need the students' help the most, the number of students needed at each location, and what work will need to be performed when they arrive. The solution we designed is to provide community gardens organizers with data that will assist them with informed decision-making and increased crop yields.
A brief overview of my job was to configure various sensors for them to accurately collect data on a regular basis and neatly package that data to be ready for the database. This diagram represents the layout of our first iteration of the garden system. It would all start with the data collection at the Raspberry Pi stations, which would then access the internet over Wi-Fi and pass through the data gathering engine. Afterwards, it would be imported to the database and through the web server, which would grab that data and provide it to the user. In this first phase, each step was the Raspberry Pi doing the processing. Here in phase 2, it will once again start with the data collection at Raspberry Pi stations. These stations would then access internet over cellular connection and pass through an AWS virtual machine. Inside AWS, the data gathering engine, sensor database, and web server would work alongside the other. The basis of the sensor suite I created was the Raspberry Pi 4, a microcomputer capable of carrying out many tasks. It was picked particularly for its GPIO, general purpose input-output, as well as the Linux-based operating system role. The DHT11 was the main sensor chosen for its temperature and humidity reporting capabilities, at a low cost of about $3 a piece. Additionally, a generic capacitive moisture sensor was used, which was also pretty cheap. Here were all the sensors working together. They were attached to a breadboard for rapid prototyping and future modifications. In our more permanent solution, this will be placed inside a robust waterproof casing. The image pictured is a screenshot of my monitoring webpage. I created it so I could remotely observe fluctuations in temperature, humidities, and moisture levels, as well as the respective time it was recorded. I was able to use a localhost web service called Apache, and therefore was able to navigate to the machine's IP address and view this. This will not be included in the final website for consumers, but it's just for debugging purposes. This has been very helpful in the development process, as I've caught flukes early on that needed to be addressed. Shown here is the terminal of AWS Cloud Computing Machine. Currently displayed is the CSV file that the sensors from the Raspberry Pi compiled. It contains the temperature, humidity, moisture, and respective times it was collected. This file is uploaded to the database every 2 minutes for recent data access. As for the next steps with hardware, we would like to integrate data from the Davis Vantage 2 Pro, a full-fledged weather station. This will be used in partner with Weewix, which is a highly customizable, open-source weather software. In order to do this, it will require an export from the Weewix database and current Raspberry Pi sensors to be compiled into a neat CSV file. We could then utilize the vast amounts of collected data and intricate graphs for more sophisticated analysis. Pictured on the left, you will see the Weewix graph displaying each piece of data it has collected. There are actually over 12 graphs of data in total, but they are not all pictured here. On the left is the Davis weather station in action. It is equipped with a solar panel, a battery, and more. On the right is a picture of the inner workings. This is where additional Raspberry Pi sensors will be stored and protected from the weather. Other devices such as the cellular modem, batteries, voltage regulators, etc. are here to make the station self-sustained. This is necessary as the garden may not have any Wi-Fi or power outlets within reach.
The database for this project will include 5 tables, with the possible additional table added used for video that are connected through relationships. Due to the multiple components and variety of data being collected in 2-minute intervals, importing the data based on the sensor type and category in its own table was the best approach. With the vast amount of data being imported, using the relational approach will help in making the structure more efficient through establishing a connection between paired tables, refining table structures, and minimizing redundant data. This image shows the number of tables that the database currently has, with the possible camera footage table being added. To begin, we collected data imported from the weather sensors in 2-minute intervals, shown here. As the project progresses, we will have more data gathered from a more advanced soil sensor, irrigation system, and possible camera footage. The data shown is data imported from the weather station's CSV file. After eventually creating the correct script and making proper changes for a smooth importing process, I was able to import about 29,000 rows of live data collected in 2-minute intervals from the sensors, with more to come. I started off my initial implementation of the SQL database using MariaDB installed on a Raspberry Pi. This was helpful in finalizing the schema and script for building the database. As we moved forward to Amazon Web Services, I was able to transfer my script into an EC2 instance where I installed MariaDB.
At the core of our dynamic web application, we're using HTML, CSS, Bootstrap, and embedded JavaScript for the front end. And for the back end, we're using Node.js for server-side scripting, as it is lightweight, has low latency, and highly efficient for scaling. Node.js is used to bring in data to the website from the MariaDB database. We're hosting our application on Amazon Web Services EC2 instance for increased flexibility for remote collaboration. Here's a little snippet of what our site looks like. Here we have 3 example communities with data being pulled from the database and then displayed for various factors like sunlight, temperature, humidity, soil moisture, and the status of the water pump. Data has been translated to an actionable, user-friendly format for quick viewing. We're currently in the process of expanding our application to have more features, including enabling weather alerts for rain, extreme heat, and wind. Each community would have multiple plants for which we would have detailed statistics for better monitoring of the plant health. Another feature is enabling Wi-Fi capability and adding remote command and control capabilities, which include manual and automatic control of watering systems. Lastly, we want to launch a mobile app version of our application for increased portable control and monitoring. Our project is not only limited to community gardens and has various far-reaching applications. Our remote sensing weather station would help professors continue their research in the field of agriculture and animal science, especially during these times of remote work. We also aim to give back to the broader community through contribution to weather aggregation sites. Our project also aims to help repurpose space post-COVID. Offices and industrial spaces that will likely be empty due to remote work would work as vertical gardens to increase locally sourced food. Data protection and data privacy are at the forefront of our application. All the data collected would only be accessible and viewable by the technical team of our project and the end users. The data collected would be stored for year-over-year comparison for trend building and predictive modeling. This is solely to help the user gather actionable data on their plant health and make informed decisions. While the technology does support it, we have refrained from using any cameras without user permission to protect user privacy.
Gardening is something that anyone can do. With the help of our garden system and the surrounding community, we can help encourage improvements of food security after scaling this project up to be a source for produce. And for current gardens, this can reduce blighted areas and may improve operations and create a closer sense of self-sustainment.